We're going to deal with a word problem today, and the problem is that if you take Joe's age and you square it and then you add that to Megan's age, the sum you get is 76. And if you take Megan's age and square it and then add Joe's age, you get 152. And the question is it possible to find their ages? And if so, what are the ages? So we're going to formulate this problem into something that we can actually solve. So we're going to let Joe's age be represented by a J, naturally, and Megan's age be represented by an M. So we've been told that if you take, sorry, let me change the colour of my pen from black. If you take Joe's age and you square it and you add that to Megan's age, you get 76. And then also, if you take Megan's age and square it and you add Joe's age, then you get 152. Okay, so this looks like a tough pair of equations to solve algebraically across the real numbers, but there's some important bits of information in the problem that mean we can restrict this down massively. So first of all, because we're dealing with ages, we know that we're only looking for natural numbers. So does that mean we should try all the natural numbers and see what works? No, because we have another nice property in that we're dealing with squares and all the terms are positive because they're ages. That means whatever these numbers are squared has to be less than the total sum. Okay, so that means we've got a discrete set of values that J and M can take. So we're going to look at those now, and then all we have to do is test within those values to find our answer, if indeed there is a possible answer. Okay, so J squared has to be less than 76. So J is in the set of values 1, because 1 squared is 1, 2, 3, so we're up to 9 now if we're looking at the squares. 4 squared is 16. 6 squared is 36. 7 squared is 49. 8 squared is 64. And 9 squared is 81, which is greater than 76, so we cannot have that. Okay, so J takes values in here, and we can use these and try sub all of them into this equation and see if we can find M, but we're not going to do that just yet. We're going to find a bound for M as well. So M is in the set. That's terribly drawn, but anyway. Also 1, 2, 3, 4, 5, 6, 7, 8, 9. That goes up to 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. So I should write 12, not 144. And 13 squared is 169. So M can't be that. Okay, so looking at this, if we take M squared to be any of these small ones, for example, say 5, there's no number big enough in the set of possible J's such that M squared plus J is equal to 152. So we're going to start from the large end, because we're going to be looking at one of these values, if indeed any of them work. And it turns out if we take M equals 12, so we're just trialing this, M squared is equal to 144, and that implies that J is equal to 152 minus 144, and that is 8. So that is our solution. The point of this exercise was that you can break down puzzles sometimes using the information so that you don't have to rush in straight away, try and solve the problem directly for M and J using analytic methods. Instead, you can think about what are the logical and possible values and then deduce from that your correct solution. So Joe is 8 years old and Megan is 12.